Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Welcome to the live stream. Another episode 14 now.
14
of Ask Us Anything About Electrochemistry.
There have been so many. We just keep going.
And it seems like every time we do this, we're in like a different location or a different setup.
That's right.
We're always playing. We're always trying to improve upon it. For those of you who this is your first time, my name's Alex. This is Dr. Neil Spinner. We're both electrochemists at Pine Research. We get a lot of technical questions, both from our webinars, live streams, emails, phone calls, all that kind of stuff. And sometimes a webinar or a comment on a YouTube channel is not the best way to answer such a complex question. So we create these live streams where we'll really be able to spend a little bit more time diving into some of the more technical questions you may have about electrochemistry. So in this form, we're using Restream as an encoder broadcasting platform to stream, to live stream to YouTube. We've observed maybe like a 20 to 30 second delay between what shows up, what we see in the chat and what we say. So just keep that in mind as we answer questions. If you want to ask a question, please ask one in the, just type it into the chat and we'll try to get to it as soon as possible. Remember, you can ask any question that you want. There are no dumb questions in electrochemistry.
There might be dumb answers though.
There might be dumb answers just from us, just like whatever we can. The more specific, like there's some questions we've observed after doing this for a few times that we need as much detail as possible. We can't answer like, oh, why does my data look like this? It's like, well, we can't see the data. But if you're asking about like, what's the difference between a Bode and a Nyquist plot, like fundamentally, and what information you can get from it, we might be able to help you a little bit more with that. Also, apologies ahead of time. We're Americans. We might not be pronouncing your name correctly. This is also YouTube, so you can actually type in whatever name you want. One person was actually a Pokemon name. I didn't even realize it. So if we mispronounce your names, we're very sorry about that.
If I mispronounce a Pokemon name, I don't apologize.
Yeah.
I don't know anything about Pokemon. And I don't make apologies for that. So
yeah. So give us feedback in the chat. We're aiming to do this based on as many questions as we get, and typically we run it for about 2 hours or so on Fridays at 1 p.m. Eastern time. So I think I've covered all the bases.
Yeah, I think so.
Also, just a shout out to all of our members, our YouTube members, Tier 1 and Tier 2. We will provide a little bit more priority to questions from our YouTube members when it comes to answering questions. That's something to keep in mind. And if you're not familiar with it, we have a YouTube channel where you can just watch videos, but we have webinars and extra content for YouTube members. And so you can, if you want to join and support us and help us create more content like this, we would always appreciate it.
Yeah. All right. I guess I'll get to a few questions as we were getting going here. Let me see.
Yes.
So the first one, there's two questions here by Abhijit. And the first was just about taking EIS at different potentials versus OCP or versus ref. I think basically your question is, what do I take impedance versus? So I actually get this question a good amount. And I always find that this is a question that is, it means that you're not thinking about EIS, in my humble opinion, in the way that you ought to. And that is somewhat similar to any electrochemistry experiment you would ever do. And so what I mean by that is, like, so Alex and at least 2 or 3 of these have answered a question similarly to, like, what limit should my CV be? Like, and you've talked about that process of, like, trial and error getting to where your CV potential limit should be. It's like, oh, I'm doing CV, I'm going to see some peaks. So it's like, well, I'm going to scan from like 0 to 1. Well, that's not far enough. I'm going to go -1 to 1. You know, you sort of iterate and figure out that. It's like, why are you doing that, right? You're doing that because you want to see where the thing of interest is. Because if you just go at OCP, there isn't much happening. So apply that same logic to EIS. Where are you doing your EIS at? Well, what are you trying to look at? If you're just trying to get a lay of the background, the lay of the land, whatever you want to say, do it versus OCP. You'll get IR compensation, you'll get double layer capacitance. You know, every system is like different, right? But you're going to get that information. If you want to study a Faradaic process, pick your set point versus that Faradaic process. And then as far as versus ref or versus OCP, that's just moving the x-axis, my friend. That's all you're doing, right? 0 versus, silver chloride is a different amount versus OCP, whatever your OCP, like, that's just shifting the potential axis, right? If your OCP is 500 millivolts, 0 versus OCP is 500 millivolts. That's the same as 500 versus ref. It just helps to know where your OCP is if you want to polarize like slightly away from it. But all you're doing is picking the potential you want to be at. More fundamentally, the question is, what are you trying to measure? That's what will dictate where you should set your impedance experiment. And then the second question here from Abhijit was more specifically related to Pine. So while we are not doing this event to fundamentally sell our company's stuff, because this is related to our software specifically, I'll just show you briefly, Abhijit, what I think you're sort of referring to here, which is how to measure EIS in Pine. So I assume you're referring to our software. What are the commands required to get best results? So that's a tricky thing to answer like perfectly, because it depends. Again, everything sort of depends on what you're studying and what you're trying to get out of it. But let me at least go ahead and share. Did I do it? Is it working?
Yep.
I gotta maximize it though, right? There.
Yeah, there you go.
This is my first time with Restream. Alex used it last week.
I used the last one.
And it's cool. I really like it, but now it's like I'm learning all of the buttons and things. Impedance in here. So like, what are the main commands? So I'll give you a 2-minute, hopefully quick. And I know that if you're not familiar with our software, this might be like, I don't know exactly what I'm looking at. So if you're using our software, our potentiostats, this is what you might see for the setup of an potentiostatic impedance experiment. I'll just hit autofill, just plug in some values right away. So my advice, generally speaking, conditioning period, ignore it. You don't need it most of the time. 0 seconds means it actually doesn't matter what this number is. 0 seconds, it's going to ignore it. Okay. So we'll put that back to 0 because that's ridiculous. OCP, somewhere between 5 and 10 seconds is probably fine. If you do OCP measurement in your impedance and you find that it's really drifting a lot, you might need longer. Also, while we're doing this, where is the thing to put? Is it this? Oh, you know what I mean? We can put our little picture on the bottom. How do we do that?
Oh, our picture. I think
Also, I'm going to hide Abhijit's question so we don't.
Let's see.
Is it?
So if we don't maximize.
Oh, so how do you get rid of yours?
Yeah.
There it is.
There we go.
Which button did you press? I'm just curious.
Oh, I pushed it's a little like circle. That's the toggle that goes kind of back.
So
yeah, that one.
Just toggle it. So there we are in the bottom.
Yeah. So now we're here in the bottom.
Okay. Just like if I move my hands, you can actually see me. I know it's small, so maybe you can't see me too much. I'm sorry to divert a little bit here, but I was curious how to do that. Anyway, so OCP, as I said, probably 5 to 10 seconds is plenty. You're watching the experiment to see if it's like flat, stable, relatively. If it's drifting, it's a good idea to have more time. Also, if it's drifting for the entirety of your OCP experiment, you need to probably check out your system. Something might be unstable, nonlinear. You might want to not even continue running the experiment because your impedance data might be bad. Settling period, also probably something between 5 and 10 seconds is sufficient. This is just where you're picking, as I said, what are you trying to study? Pick whatever your potential is, whatever you want, whatever you're trying to study. Most systems, 5 millivolts peak. That will probably be your basement. That's probably the lowest you'll want to go for most typical kinds of systems. Usually anything smaller than that, it'll be pretty noisy. You won't get enough signal. You can usually, again, with most systems, go up to about 20. Starts to run the risk of getting nonlinear if you go too much bigger than that. So somewhere between 5 and 20 millivolts amplitude is probably fine. And then a good range of frequencies to choose, 1 megahertz to 0.1 hertz, do 6 points per decade. It's relatively quick. It'll be over. You'll get a decent survey of your system with those frequency ranges. You probably won't need the first decade. You very well may not need the last decade, but it's good to do it. If the data are not super great on the ends of your impedance there, no big deal. Don't, exclude those data from your analysis or something like that. But that would be my suggestion for you of in aftermath, like what to do, etc.
Nice.
Okay.
That's good.
So did you want to get to Pete Venuti's question? I think we had a question from.
Well, we can get to Pete. I'm looking at, so we get for those like we usually put the live stream schedule ahead of time, so you can even put questions there ahead of time if you want them answered.
That's right.
But there's also, I know that there's people who are here now who are listening. I didn't know if you want to just go in order, because there's Ferris Whitehouse for the question, and then Kempor asked the question, which I can answer as well.
Okay.
So either one is fine.
Why don't you answer Kempor's question, then I'll get to Ferris's question.
Sure. So Kempor just asked, is there an indicator solution that tells an experimenter when an electrochemical reduction or oxidation is complete? So generally speaking, there's no chemical solution, sort of say, or a chemical that you can add. It'll always, and actually Chris just made a note, which who just said it would be the chemistry would be very system dependent, which is completely correct. So there's no chemical indicator to let you know whether a chemical reduction or oxidation is complete or not. However, there are some things to know if, say, you're doing a bulk electrolysis experiment. There are a couple of things you can do to determine whether or not you've completely oxidized or reduced the species in solution. So I'm going to try and share my.
I don't have to unshare myself before you can share.
No, I don't think so. I just need to make sure PowerPoint is max, and we can just always double check. So yeah. I'm just gonna go.
That looks good.
Here,
I'm gonna get rid of the question on screen so we can see it.
So we can see it.
Oh, I'm gonna unshare my.
Yeah, there we go. Cool. Okay, so let me go here, and then I believe he'll send you a review. So there is. So when you have, say, a system, and I'm just going to say, let's say you start with, make sure I have a decent thickness. So most people who want to know whether an oxidation or reduction reaction is complete, they're actually referring to a system where they have a solution and they have their redox, they have some 3 electrode thing, maybe. Okay. And then they have maybe a reference or something here. I'm not the best artist, but you're doing some kind of electrolysis and you want to know when it's done. So you have a stir bar at the bottom. So the kind of experiment a lot of people might do for these kinds of things where they're completely oxidizing or reducing a species is a technique such as chronoamperometry or chronopotentiometry. I have to
I have to say it
the way it's pronounced so that I spell it
correctly.
Potentiometry. Yeah.
It's what's what my favorite unit of measurement is? It's the one around a rectangle. It's the perimeter.
The perimeter.
Yeah. Perimeter.
Oh, the perimeter. Yeah,
Yeah,
perimeter.
no, there was a girl when I was I'm this is not
Yeah, yeah.
relevant, but when I was in high school, I think, and I was, in whatever class or whatever, one girl in my class raised her hand and was like, I know what a kilometer is or whatever. What's a perimeter or something? It was like we're all
Oh,
just like,
perimeter.
oh my gosh, really? Okay,
That's
awesome.
great.
Yeah, I found that funny.
So you can use both. So one way when doing some kind of electrolysis where I'm completely oxidizing or completely reducing something is some people may use a technique like chronopotentiometry, where it's a galvanostatic technique. So we set the current. So I'm going to go back to using text box. So in this, we are set the current. So and we control the current. And what we end up seeing more often when we're doing this kind of thing is we have time, and then we have voltage when we do chronopotentiometry. So if we set the current to something like a milliamp or 20 milliamps, you're setting the rate of a reaction. And as you're stirring, you have your redox species in solution kind of getting near the electrode surface, and then it's getting oxidized or reduced. And what typically happens is that over the course of your experiment, the voltage starts to, it stays relatively the same. To maintain the current that you have in your chronopotentiometry experiment, to get it, it just has like, oh, I need to, I get the same voltage for this reaction. However, at a specific point, at a specific time, you're going to oxidize or reduce all of those molecules of interest. But your potentiostat is going to try to adjust or change the voltage in a way so that it can maintain that current, which means the voltage may go up or it may go down. Or sorry, I said that wrong. Voltage may go down or it may go up, depending on which way. And that means that the potentiostat acting as a galvanostat is now kind of oxidizing or reducing something else to get that current to run. So this is the indicator. It's not a chemical indicator, but once you do a chronopotentiometry experiment and you notice that the voltage is no longer constant and it's starting to go either up or down by quite a bit, you know that you've oxidized or reduced all of your analyte in solution, and now it's doing something else. So I hope that was helpful.
That's a great answer. And
chemical.
actually, to bring it to batteries, which is what like everybody keeps asking about, apparently.
Yeah.
What you just described is like a very concise explanation for a charge discharge for GCD, basically.
Oh, interesting.
So when like you can think about that in the same way when you're charging or discharging a battery, you're doing galvanostatic charge or discharge. It's just chronopotentiometry. That's all it is.
Yeah.
Right. You're applying the battery curve goes up or whatever, or it goes down. But most of the battery charge discharge is exactly what you drew. It's flat.
Yeah.
Mostly flat. It changes ever so slightly. But when
Mhm.
you're discharging a battery, it's mostly flat. And then after a while, it falls off a cliff.
Oh, interesting.
Because exactly what you just said.
Yeah.
It's a perfect explanation of what is happening in that situation is what you just said.
Oh, okay.
Because you've discharged everything, right? You've used up all of the lithium in the anode or whatever, right?
Mhm.
And there's no more. And so the indicator, to your point, to
Yeah.
your question, Kempor, is that the indicator that the reduction is complete, so to speak, or that you've used up everything, is the voltage falls off a cliff or goes up or whatever.
Yeah.
So that's exactly
okay.
an explanation. You've inadvertently described battery charging and discharging.
That's
It's
good,
exactly.
I don't understand batteries that much. I need to know
well,
more.
you do. You just
I
don't. You don't know.
I just don't know it yet.
The terminology is different and stupid and weird, but that's exactly what's happening. You literally described it to a T.
That's good.
So that's really good. Yeah.
Very good. So Kempor, let us know if that was clear and if you need any further explanation about that. Hopefully that's helpful.
All right, I'll get to Ferris's question now. So Ferris has asked this question: can you recommend a technique for measuring the crossover of redox species through a membrane in a flow battery? If the crossover was significant, could it show up as a feature in a Nyquist plot? So the tricky thing about your question is to measure the crossover of a redox species. electrochemically, probably. I'm not the best at knowing like what, like, so the crossover, like there's two ways that you would want to, I suppose, potentially answer this question. One would be in a general way to say, I can deduce from my data that there was crossover of X species across my membrane. The other would be if you're trying to quantitatively answer that, to say that there was like X moles per square centimeter per decade, per year, per minute, like, right, like crossover could be like an amount of stuff moving per surface area or per time, right? So there's two, I don't know, levels of depth that you could go through. That quantitative answer, like, I have no idea. There's probably a way to do it, but you would be correlating like electrochemically current voltage, right? Like, that's a little bit beyond me. I don't know, to be honest. It might be someone might have done it. Maybe it's in the literature somewhere. More generally, though, you talk about things like crossover rate, and honestly, a lot of the times it's more qualitative, and they talk about things like water crossover. So you might be talking about like a charged species going through like a Nafion membrane is a proton shuttle. So in one sense, this is a question about like how many protons are going through my Nafion membrane, or how do I have two systems where the electrochemistry would tell me whether one has more or less, something like that, right? So that's a more general question. In some sense, the answer, let me try to think. In some sense, the answer is captured by the electrochemistry data itself, because if you have a system, let's just say, where for one reason or another, that the limiting step is the diffusion, for sure. Now, that's not always the case, which is tricky. And in fact, with like a PEM fuel cell, and I'm making an assumption about something that I know pretty well, which is like PEM fuel cell. So your system might differ, right? You might be using an alkaline fuel cell or something else. Okay. But just for example, with a PEM fuel cell, one of the things people do is they take their Nafion membrane and they soak it overnight or for a while or something in acid, because you're saturating the membrane with protons, so that when you run your fuel cell and you put oxygen in one side and hydrogen in the other, you're not waiting for diffusion. So in that case, you're actually not limited by diffusion. You've already pre-populated your membrane with protons. You're not really waiting for them to diffuse. If you didn't do that, it would almost certainly be the limiting factor. And it depends on, if you do a polarization curve, there are potentials with which you can force diffusion to be the limiting factor. But the point is that if you had a system where, for example, you knew diffusion was a limiting factor, or at certain conditions, like certain applied voltages, then part of your answer might be two different conditions. You change a variable. One of them gives you more power or more current or a better electrochemical performance. That is in some way a mildly quantitative method, I would say. In other words, it's not quantitative in terms of how much stuff per area per hour, but it's quantitative in terms of I got 10 milliwatts versus 2 milliwatts. So there's some quantitative answer. That is some way of saying I got better crossover because my performance was better, right? This one performed worse because I was waiting forever for stuff. So that's kind of one answer. And then as far as showing up in the Nyquist plot, the last thing that I'll say about this is that I guess I can share my PowerPoint and just draw a thing. PowerPoint, that's the one. And then there we are. Okay, I'm going to hide this. So one of the things that I have talked about in the past, I've shown this in some of my webinars and stuff like that. In a Nyquist plot, for example, for fuel cells, you often get, again, not always, but you often get something like, you get like one semicircle for like sort of IR compensated charge transfer, some sort of process like that. And then sometimes you get a thing that looks like this. And so you have this sort of 45-degree angle here, and then it's kind of a semicircle. And basically this is like a Warburg short element. So effectively one of the kinds of circuits that you can fit a fuel cell with is something like this. Again, not always. It depends on the system. It depends on a lot of stuff. But roughly speaking, you have some sort of uncompensated resistance. Maybe not, because if it's a two electrode system, that's actually not really totally accurate. I'm just like, I'm trying to blast through this and not take forever. We have a lot of questions to get to. The point is that this is kind of like the fuel cell process, whatever it is. It's the oxygen reduction reaction, or it's electrolyzer or whatever. And this Warburg short in a Nyquist plot, sometimes when people have seen this, what they've attributed to is water flooding or uptake or crossover, something like that. So sometimes, for example, the difference between like this and that, right, can be this diffusion layer, this finite length diffusion layer, and it can be an indication of crossover of water in particular, as I said, through a membrane. So, and I don't know enough specifics. Like I said, if you look in literature at some of these papers where they've done stuff like this, I'm not sure if they correlate that with like quantitative amount of crossover or quantitative amount of water, or they just sort of say that's the reason for it. That requires more investigation that frankly I'm not I don't know enough about to comment on further, but that's the best that I can tell you regarding that question of crossover. And then beyond that, as Alex has always said, it's like if it's related to a specific system that's not a PEM fuel cell, but I'm sort of just answering based on what I know, best for me, then we would have to figure that out based on seeing your data in particular, which we can't do now, of course. So
yeah. Well, I think that was very helpful, and I think just from listening to you, it sounds like okay, diffusion is the main kind of culprit with like crossover and the measurement of crossover, and the Warburg elements are the ones in Nyquist plots and in EIS that contain that diffusion information. So if there was crossover, it would show up in the Warburg element of the Nyquist plot.
That's probably a good distillation of that. Yeah, for sure. In one or whatever the Warburg, whether it's finite, infinite, right?
Yeah.
Whatever. That's probably a good synopsis of that. That information will be captured probably in a Warburg element of some type, or a CPE. If it has like an alpha of not exactly 0.5 or what have you. So something in that nature. Yeah, that's probably fair.
So it looks like we got a couple more questions just in the chat. And we can look through them. Let's see. So Shadab is asking how to measure capacitance from Nyquist plots. So luckily, I think that's a relatively straightforward-ish type of thing. At least today, the way one would measure the capacitance from a Nyquist plot is you really want to use circuit fitting.
Yeah.
You could, in principle, try to calculate the impedance mathematically and looking at all those
from a Nyquist
dots,
plot. You could not. It's not physically possible.
Oh, it's not physically possible. Yeah,
not
just
really.
Mathematically, it would be just it's not very possible. So, so basically, I think
let me show an illustration.
We can show
of why that's
aftermath.
Not possible. Yeah, I'm going to share.
Just why it's not possible. Like if someone has any Nyquist plot,
I'll give you.
There's no.
It's not. You can't quite do it. That's why circuit fitting
is the way to do it.
Yeah, I guess I shouldn't say it's totally impossible, but it is much more difficult without circuit fitting to do that. Did I share the screen or did I not?
I didn't maximize it. That was to share the screen. I'm gonna hide the question for now.
Thank you. Yep, and put us.
We're gonna show our little.
So here is a quick example of a Randall's element. Okay. Again, I'm going through things relatively quickly here. Semicircle is what you get with the Randall's element. I don't even have a leading resistor, so it's just at 0 here. The width of the semicircle is directly proportionate to the resistance. So the one thing that you can do on a Nyquist plot is get the charge transfer resistance if you have a semicircle, right? Little circle, small resistance, big circle, big resistance. That's obvious. Now watch the Nyquist plot. Now part of the problem is because this is a line and not dots. That's just how our software represents it, okay? If there were dots, you might see a difference. But watch the circle as I change the capacitance. If you're wondering why you're not seeing anything, that's the point. So semicircle, unless I go very, very far, very large, it doesn't complete. And if I go the other way, you'd see something like this. This is not anything you'd probably see in real life. But the point of this is that what Alex said is true. Circuit fitting is really your best friend, because just looking at a Nyquist plot, what is actually happening here is that the distribution of points along the semicircle is changing, but the overall shape of the semicircle, that's some thunder. Is that
Yeah,
thunder?
we're in North Carolina.
All of
We
a
just heard
sudden,
some thunder, and
I was like, is someone moving something upstairs? Good
yeah,
Lord.
I thought our colleagues were maybe fixing the doorbell or something
Yeah.
like that. But now I'm like, oh no, that's
It's just the impending apocalypse. Don't
impending
worry, everybody. We're
apocalypse.
okay.
It's all good.
Gosh, that was loud.
That was very
I can hear it through my headphones and
Yeah.
everything. That was a little scary. I'm not going to lie.
Yeah.
Okay. What was I talking about? Yeah, capacitance.
Oh yeah, capacitance and Nyquist plot, and
Good grief. So
changes
So
the-
in summary, the points along the Nyquist plot are clustering either more at the beginning or more at the end, but the shape of the semicircle is the same. So just at a quick glance, you see a semicircle, you can't really deduce what the capacitance is. So circuit fitting is really going to help you there. You're going to want to do circuit fitting. There are some mathematical ways to do that, but it is not quite so easy, right? It's a very quick, easy way. There isn't a very quick, easy way, I should say, to deduce the capacitance just from a Nyquist plot. You can do there's like a peak thing. I've done this in my webinar anyway. I'm sorry to kind of brush off completely here. There are some, like, you can get the peak of the Nyquist plot that correlates with the time constant. You can sort of back it out.
Yeah.
But that's a little convoluted, to be honest, and that's the point, right? So circuit fitting really is your best friend.
Yeah. And this is also just an RC circuit.
Yes.
Like, we don't even know what you have. Like, even the traditional 3 electrode cell is a Randall circuit at its simplest estimation of your electrochemical system. So it's much better if you use fitting software.
Yeah.
And then you have other questions about all the other capacitive elements as well.
Yeah.
So Shadab, I hope that answers your question. It's really important to use fitting software to measure the capacitance from a Nyquist plot.
Yeah.
Going ahead, let's take a look. Oh, I'm in the wrong thing. So Sadaf is asking, hi, is it possible there occurs redox reaction in negative potential window for, looks like a nickel molybdenum oxide in sulfuric acid? As the literature reported, the redox reactions of N2 plus in positive potential window. Well, I think we'd probably have to do a little bit of a literature search on this. Nickel really, it's mostly like the +1, +2, +3 are the most generally observed oxidation states for nickel.
So I did my PhD with nickel.
Oh, okay.
But
so
it
you
was
may know the most about
but
it.
it's nickel is most commonly used in alkaline systems.
Yes. Okay.
And that's what I did. So right now, what I'm doing is looking up a table of. See, is the question about?
So
does it occur in a negative potential window? Okay. So your question is if it's in a negative potential window. So,
also, you're in sulfuric acid. You might start reducing hydrogen before you start reducing nickel.
So
one,
yeah. The two things that I would say first of all is that, as your potentials shift inversely with pH, which is to say, as the pH goes down, the potential something happens goes up. So what Alex said is going to be the case more acutely in your system. If you're using sulfuric acid, let's just say it's 1 molar, your pH is like 1 or 0, or it's low, right? Let's just say it's 1 for argument's sake.
Yeah.
Potentials shift basically minus 60 millivolts. This is from the Nernst equation.
Yeah.
Potentials shift 60 millivolts per pH unit. So if you go from neutral pH to pH of 1, you have 400, right? 400 millivolt shift. So for example, something that would happen at 0, millivolts at neutral pH, for example, when you go from pH down, it's going to happen at positive 400, which means that when you're at 0, you're actually like 400 millivolts, even more negative than you think you should be, for example, which means that as you start going really negative, you might just start ripping apart water and producing hydrogen, as Alex said. The other thing is that be sure that whatever redox you're seeing is nickel and not molybdenum. Molybdenum has a lot of different oxidation states. Nickel doesn't have as many, to my knowledge. Nickel's mostly a +2 or +3, and it's usually an oxidation thing, because you go from, those happen in alkaline at positive potentials, which means they,
Oh,
but yeah, like you said, I think you just look in the literature for some
Yeah,
opportunities here, and make sure that you know what you're seeing oxidize or reduce. Is it really nickel or just something else?
so if it's positive potentials in alkaline systems and then they're going to very acidic systems,
Yeah.
you think it's going to shift it negative by, you said 400 millivolts was maybe the maximum range.
Well, that's for 7. If you don't, if you go from 14 to 1, it's 800.
Oh, then it's 800.
So if you go from pH 14 to pH 1, you're going
Yeah.
down. Everything shifts even higher,
yeah.
right? So if I go from high to low, right? I go from high to low, the potentials go up. So if they're already at positive and I go to acidic pH, it's going to go even higher,
Yeah.
right? In theory, it shifts up. So it's like if I'm doing like KOH nickel
Mhm.
electrochemistry, and I have something happening at 0,
Mhm.
and then I go to acidic. Forget for a second that like the electrochemistry is
Sure.
probably fundamentally different.
Yeah,
if
that's
we're
right.
because like the reactions include hydroxide and whatever. So
Right.
now I'm in acid. In theory, that same reaction would happen at 800, not at -800. It would happen at positive 800.
Yeah.
So it's like we're going in the wrong direction for
Yeah.
what might be happening in negative potentials.
Yeah.
pH is 0.66. Yeah. So we've got some. Oh, sorry, that was a different question.
Yeah.
That's different person.
Yeah.
Just happens to be talking about.
Yeah. He also talking about pH.
Yeah, I think ultimately you're going to need to cross-reference with literature, and I know you said that you've seen this literature reported. But with yours, be sure that what you're seeing is what you think it is. Is it really nickel, or maybe? I mean, you have a molybdenum thing. It could be the molybdenum that's reducing, or
That's
whatever. That's a possibility. But also, I'm a little skeptical because nickel is typically used in alkaline. It's not as commonly used with acidic systems.
Mhm.
So perhaps something is going on there. And then molybdenum certainly has a number of different oxidation. For example, I'm even just looking right now, molybdenum will react. It's an alkaline reaction. There's probably an equivalent acidic one. But for example, molybdenum oxide, O4, will react. It's like a 6-electron process at like -0.9. It produces hydroxide, so I don't know if that's even possible in acid. So, but
Yeah.
I'm just looking at molybdenum, and it has some, standard potentials in minus range. So perhaps the molybdenum is what you're seeing. Just a thought.
Yeah. Another thing, Sadaf, is that I think one of the most important things that Neil mentioned is that the chemistry itself is going to be different
Yeah.
in these ranges, and really changing the pH has just shifted like almost the measuring tool, sort of say. It's
Yeah.
like fundamentally going from a nickel molybdenum oxide from a alkaline to an acidic solution fundamentally changes like everything. The scale that you're using in some ways is arbitrary. One thing that it's kind of hard to wrap like even I have a hard time wrapping my head around this, but like positive and negative potentials don't necessarily always mean negative and positive charge.
Yeah, that's true.
So even though they've shifted to a negative potential window, it doesn't mean that positive charge is not on the surface able to do things.
Yeah.
Just because you're shifting that position.
Potential is completely relative. So
Yeah,
you
it's
change the reference
relative.
electrode. That negative potential is now a positive potential, but it's the same process.
Yeah.
Yeah. So we get locked into thinking that like it's a negative potential based on whatever I'm using. It must be a negative charge. It's like not necessarily.
Yeah, not necessarily.
Yeah.
So just keep that in mind when thinking about this question.
Yeah.
All right. So hopefully that was helpful.
Okay.
All right. Chris Georgie, is there any method which uses an additional pH reference electrode to help correlate diffusion rates or diffusion rate? I don't think so. Well, most
additional pH reference. Do you mean a pH probe or a reference electrode? I guess I understand what you mean by additional pH reference electrode. So like if you're in an alkaline system and you're using an acidic reference electrode, or do you mean like a pH probe that's measuring the pH? I don't know what that. I don't know what that means. In other words, I don't know what you're asking. Like that,
Yeah,
that's,
most diffusion measurements are kind of reference electrode independent.
yeah.
Just as we said, like kind of from the earlier questions, like, oh, we're just shifting the potential around. But like if when people use electrochemistry to determine diffusion coefficients, it's always the utilization of the current that's actually part of the measurement that's needed for
Says across
diffusion
a membrane.
coefficients. Or you think this is related to the
He's
crossover?
no, he just said across a membrane.
Across the membrane.
He says, so is there any method uses an additional pH reference electrode to help correlate diffusion rate? So you're asking,
Oh, like maybe maybe like an
Oh,
H
like
cell
a-
configuration.
no, I think what you're saying is like, okay, if protons are crossing over, one side's going to get more acidic over time.
Yeah.
something like that.
Oh, yeah.
So
Is there a technique?
is there a technique? Maybe. The tricky thing about that would be sensitivity. For example,
Mhm.
like pH is the minus log of the H plus concentration. So you
Right.
could, in theory, measure the pH on one side over time or whatever, and then correlate that to a H plus concentration. And then you are getting some measurement of the change over time. So that could, in theory, be the case, but you would also be ignoring possible effects on pH from like anything else, because you have
Yeah.
redox happening at those reactions that could be affecting it. So I think that's possible. I'm not sure that's a slam dunk answer. Like I think it's a good idea. I wonder how easily it would be quantifiable though, because you're making an assumption that any change in pH that you'd be measuring across one side of the membrane is correlated only with the crossover of some species and nothing else. And maybe that's the case.
Yeah,
And
you
that
might
would be
be able
great
to
if
do
it's
so.
the case. I mean, if it is the
Yeah.
case, that would be really wonderful to be able to make that correlation. But
Yeah.
I guess that's probably what you're referring to. And that's a cool idea. I guess I'd say you have to give it a try
Yeah.
and see if your assumption is accurate. But I'm not sure that assumption would hold up perfectly. So I don't know.
One thing that one thing to keep in mind, this isn't really an idea, Chris, but like when we measure diffusion coefficients using cyclic voltammetry and other electrochemistry techniques, it's very potentiostats are really good at measuring current. Voltage ranges tend to have a little bit less resolution, and you're mostly going to be, and the pH change, like if you went from say, so I have to go from pH 1 to pH 0.1 to see 59 millivolts of difference, right? So if I want even higher resolution as I'm measuring over time, like yeah, a whole pH unit might change, but like I'm only measuring like maybe only a small amount is happening over that time frame. So
Yeah.
there
And
may
you're,
be some
and you're talking
accuracy
about like,
things.
well, I have 59 millivolts across a pH unit. And so if I change by 1 millivolt, that's 1/60th of a change, like whatever. But
Yeah.
there's no instrument that gives you 1 millivolt. I mean,
Well,
like the accuracy is in question here. So like
yeah,
it changes
yeah.
by 1 millivolt. Are you sure that's not just the weirdness of electrochemistry, or it's exactly because of your pH? Like that's not enough of a change that you can trust, for example,
Yeah.
right? Like so that's yeah.
If your potentiostat has
Yeah.
incredible microvolt resolution, and it's not, and
But even
the
then,
rest of the system's not changing.
but that's the point. It's not just the resolution, like you said, it's the accuracy of the instrument. And a
Yeah.
potentiostat's ability to measure potential with like insane accuracy is just it's just not that good. You know what I mean?
compared
Like
to current.
right,
Yeah.
exactly. So you're trying to see like, well, how much change in potential did I get? And I'm hoping that I can, this is another one of those general advices, and we see this with customers sometimes where they like, oh, well, it's 4 millivolt different than the last time I did it. It's like, no, it's not.
Oh yeah.
Or
Yeah.
or maybe, but I
Yeah.
don't care.
Yeah.
Like you can
may
do
have
this
drift.
experiment 9,000 times and you will get 10,000 different potentials. It will never be exactly the same. That's the limitation of science.
Yeah.
Our instrument measurement and capacitors and resistors and the wonkiness of electrochemistry. You know,
Yeah.
it's like it'll never be so perfectly precise, right? This is the same across different tests. Like it'll never get there, you know. So yeah,
another
that
thing.
does call into question how easy that would be to do to quantify. But it's a
Yeah.
good idea. I think
It's
it's
a
a
good
good
idea.
idea
I
if
think
that's
it's a
what
really
you're
good
referring to. But yeah,
Okay.
so we have here.
Nana I'm not even gonna try. Sorry, Nana. So as asking is the next question. Also, for all of you who've been saying thank you when we answer your question, you're very welcome.
Yeah.
Happy to do that. I just
Thank you
know that we're getting
for
some
joining
comments.
us. We appreciate it.
How does having a solution of iron 3 plus and iron 2 plus ions at high concentration affect the electrodeposition and stripping of low concentration copper 2 plus on a platinum electrode? The ions are deaerated in sulfuric acid. I have to think about this. So
What's the potential for iron plating? Is it like what's iron compared to copper? That's my question. Copper. So if you're plating copper 2 plus, there's plating copper 2 plus on a platinum. So when you're plating copper 2 plus, for example, I'm just looking at
looking at potential.
the copper 2 plus 2 electrons goes to copper here. I'll just share this tab because I have like a potential page open here. I'm sort of looking at it and not. Let me stop sharing. I'll share this. That one. And let's max. Oh, you got it. Yeah, there we go. So this is just one of these pages here. So for example, here's copper 2 plus. This is the standard potential for copper reduction, which is plating, 0.34. So what this means is that if my potential is below 0.34, I'm going to start doing this reaction. Okay. Now, iron. No. So she said 2 plus and 3 plus.
Yeah.
So basically, okay. So either one, it actually, in theory, wouldn't matter. So here we have, from a purely thermodynamic, voltage-driven perspective, it shouldn't make any difference as long as you are lower than, where is it? 0.3419, but still above basically 0. Right? So if you have a solution with copper 2 plus and then and then iron, shh, we're doing a live stream.
Sorry.
That's fine. I was just teasing. And then you have iron 2 plus and iron 3 plus. Basically, if you're under 0.34, this will start plating on your platinum. If you go under minus point, just call this 0. This is basically 0, right? 0.03, whatever. Or for that matter, minus 0.44. If you go even less than that, you will start plating iron as well. If you are above these potentials, this reaction won't happen, right? You'll be stuck on the oxidized side. So the answer to your question, in theory, now practically, I don't know if there's some other side things that might happen. I suppose I'm not looking at every possible, reaction that could occur. You might have like, okay, this is a 1 electron process that might happen and steal some of your current. It won't plate, right? Iron 2, this is just making iron 2 plus, assuming there's no other complexes. Like I'm making a lot of assumptions, but just looking at this from a bare bones plating perspective, in theory, if you are below 0.34, but still above the potential for iron, you should be only plating copper. In theory. But yes, possibly iron 3 plus to 2 plus might be an issue for the measurement, but not for the plating. So you would have to, in theory, well, I don't even know how you would, but you would, if you're caring about how much current is going towards one reaction or the other, I don't know how you deconvolute that exactly. Maybe impedance would help. It's possible. I'm not sure. But the short answer, I guess, if you will, is that you want to be in a potential where one's happening, but the other one can't.
Yeah, I think, if you had the potential more positive, you'd be getting, what Oh yeah, you would still have it, you would go from what was it? It was copper 2+ to copper solid.
Mhm.
So that was positive. So that means it thermodynamically just happens at high enough potentials. It's interesting because it's also like it's a reduction process. Like the copper 2+ has to reduce to form it, but that's at again. Again, we're talking about like potential ranges.
Mhm.
It's like, oh, it's a positive potential, but it's like
Yeah.
here.
Well, this was the follow-up that Nana said. When we have competition, that's what Chris was just saying. That's what we just were talking about. So yes,
Yeah.
there would be some competition between the iron 3+ reduction and the Cu. Well, not oxidation.
Well,
So in some sense, you might, again, this is where you might have some current at certain potentials that is, well, okay, well, now you're asking sort of two things, right? If you're at a potential above the copper or whatever, but it's below the the iron one, you might be oxidizing copper and reducing iron at the same time. And so again, your
Mhm.
current is going to be an aggregate of those processes happening, some positive from this oxidation, some negative from this reduction, and it's going to be somewhere. Like the potentiostat's just measuring the aggregate current. That might
Yeah,
include a bunch of different processes
that's
happening
true.
at the same time. So I took your question as if I'm trying to plate copper and that's all I want to plate.
Yeah.
The answer that I gave was with that in mind. The potential that you pick should be where you're plating copper, but not where you're plating iron. That doesn't mean that you're not doing anything to the iron. And so you could have this like parasitic current effect where some of the
Yeah.
current that you're observing, I have 2 milliamps. Well, how many of those milliamps are copper plating current so that you could use like Faraday's law of electrolysis and figure out how many moles, whatever. Some of that is from iron 3+ to 2+,
Yeah,
which is just happening in solution.
that's right.
You're just
There's just
reducing.
electron exchange
Yeah,
between those
you're
two.
just reducing the oxidation state of iron, but you're not plating it. It's not plating.
Yeah.
So yes, there would be competition potentially between any and all reactions, depending on what potential you're at.
Hmm.
And generally speaking, like I said, I think you want to think about what potential to hold your system at if you're trying to just do one thing, for example, plate copper and not the other thing.
Hmm.
That would be my answer.
Yeah, I think so. And like the concentration, the concentration differences usually will refer to also the rate with
Yes.
which it's happening. So if you have more of it, you're going to get a higher current for
Mhm.
one process versus another,
Yeah.
which may actually be really good if you're applying a potential and you're getting like a small current. It's like, oh, well, I only have a little bit of copper, copper 2+, so maybe that's the only thing that's happening. But all of a sudden, if I notice a high current, it's probably because the iron 2+ or 3+ is actually plating
Mhm.
on the electrode or on the platinum electrode. So
Yeah.
that's this is at least our initial. It does get complicated when you start having these mixed species in your solution that are all electroactive. But if you did a cyclic voltammogram within a decent range, you should see if there are reactions for all of these things, and you can probably go to a chart like the one Neil showed and be like, oh, this one is 2+, or this one's copper 2+, this one's iron 2+, this one's iron 3+. Maybe those two are close together, and you can understand for your system, deaerated sulfuric acid, and then keep in mind that the platinum electrode does have chemistry on sulfuric acid. It gives this butterfly plot. So
like for example, what Alex
Yeah.
was saying is like if you were to do like a CV, you might see something like this with much better art. But like,
Oh,
okay, whatever. So
it's
like
actually very beautiful looking.
this should be way over here. Like it shouldn't. It's like tracking too high. You know what I mean? There's no split here. I didn't draw this well at all. Okay,
It's
sorry.
okay. It's all good.
The point is like if you do a CV over a big range, this might be your iron, redox here, and this is your copper one here. Okay, whatever. So the point is, as Alex said, you might consider doing something like a wide range CV, and you can sort of see the peaks that correlate to the different electroactive species, especially if they're separated by, whatever, a decent amount of potential. So that was just the point that I wanted to show there. So
yeah. So hopefully that was
helpful,
Nano, or at least gave you some information.
Okay.
All
I think
right.
we missed one in the middle here. We didn't miss, but there's one about Tafel. Shadab ask, what kind of information? There it is. I almost missed it because it was a shorter question. What kind of information we get from a Tafel plot? kinetic information.
Yeah, Tafel plots it's like I still struggle a little bit with, like, I haven't had to use a Tafel plot for like research, and I personally find like there is the like Tafel plots come from the Butler-Volmer equation, but the Butler-Volmer equation very very rarely applies to real electrochemical systems in terms of the
Almost
theoretical modeling. So sometimes but yes, you're right. You do get kinetic.
The Tafel
information.
plot, very briefly, this is my soapbox. You're gonna bear with me for a moment here.
Yeah.
The Tafel plot is one of the most misused plots in electrochemical research, because people will just do a cyclic voltammogram or a linear sweep voltammetry and make a Tafel plot, and it's inappropriate, because a Tafel plot is like you're getting a Tafel slope, and it's like however many millivolts per decade, and so your axes on a Tafel plot, when anybody shows a Tafel plot, the axes are voltage or whatever potential on the y-axis, and then the log of current on the x-axis, right? Or whatever, something like that, or natural log, usually log base 10. That is not what the axes are. It's log of kinetic current. It is baked in assumption. It's the log of the kinetic current. If you just do a CV or an LSV and you transform it into a Tafel plot, you're not necessarily accurate. You might be, but you're making an assumption that you don't realize you're making. You're making an assumption that 100% of the current that you're observing is kinetic only. There are no impacts from non-Faradaic processes, from double layer capacitance, from charging effects, from anything else, that it is 100% kinetic information. And that is almost never the case. I mean, almost never the case, right? So that's why rotating disc electrode stuff, for example, is super beneficial, and people do this in fuel cell research and electrocatalysis, because by rotating the electrode, you can observe diffusion limited and diffusion controlled processes. You can tease out the kinetic current from that. You can separate essentially the kinetic current from the diffusion limited current, and that's a process with, for example, the Kentucky-Levitt analysis, which, shameless plug, that's in our members session. I've done a webinar on that. I probably will be repeating that webinar in the future, this winter, or at least in a couple of months, but an RRDE analysis sort of a thing. But basically, short of isolating the kinetic current, the use of a Tafel plot is at best full of error, and at worst completely useless. So what can you get from a Tafel plot? Kinetic information. What are people often getting from Tafel plots? Wrong kinetic information, because it's not actually kinetic data that went into it. So be careful with Tafel plots, and be careful what you're seeing. It's not always accurate to do so. It's just a very attractive plot to make, because the semi-log kind of a thing allows you to see like changes in slope, and you can get like kinetic information, like how many electrons were transferred and how fast the reaction was occurring and stuff like that.
It was like the electron. It's like K not the heterogeneous rate. Well, I think
what's that? Yeah, it's called the
Why am I blanking out on it?
I know what you mean. I am too. It's not the. It's the hang on, I'm gonna look it up now. It's a rate constant, but it has a different name. Now it's gonna bug me too. If I don't come up with it. I have it. I only gave a webinar on it. It's not like I don't should know what it is. Hang on.
Yeah, it's exchange current density.
Thank you.
That's it. The exchange current density.
Yes.
That's something that you can get from the Tafel a Tafel plot or the Tafel equation.
Yeah.
And sometimes even that, people don't even like the interpretation of that is even kind of misconstrued sometimes. But
electron transfer rate constant. That's actually what I was thinking. Electron transfer rate constant. So that's a K, centimeters per second. That's
I'm
not sure if we're talking about different things. That's what I was thinking. You're talking about a different thing too. So
the heterogeneous rate constant is an expression of how fast the electron transfer is, and the exchange current density is also
the exchange current density. Yeah,
it's also
it's a theoretical
related, but
the exchange current density is like a theoretical thing that is how best to describe it. It's like it's a fundamental concept related to it's intrinsic to the electrode and
Yeah,
the reaction you're
and
studying. Like
yeah.
it's a theoretical current related to the process or something, which it's like at what potential, at what, I don't know. You know, like it's
Yeah.
like a constant fundamental to some baseline amount of current or something. It's sort of nebulous. It's actually you can read the definition of it and still not know what it is. It's kind of odd,
Yeah.
in my opinion, to define. I always find a hard time defining it as
Yeah.
well, actually.
It's I've tried to kind of wrap my head around it as best I can, but I think in general, it's
By the way,
like,
this is I naught, like I0.
yeah,
Like,
I
if you
naught.
see
I
I
naught
naught,
is
that's what
the
it
exchange
is.
current density.
Yeah.
But I think the idea is that it's because when you measure, it's supposed to measure how easy an electron transfer is, and so because because you're looking at over potential in a Tafel plot, you're looking at, okay, how much additional potential do I have to push to get current to flow?
Yeah.
And the exchange current density means like, oh, if something has a very high exchange current density, I don't have to apply as much of an over potential to get a lot of current.
Yeah.
But if I have a low exchange current density, the electron transfer is much harder to do. I need a higher potential to drive the same amount of current for a reaction or a system where the
Yeah.
I need a higher potential to get the same current for a different system. So the classic example is like hydrogen evolution, like reduction of protons to hydrogen, very large exchange current density on platinum, super low exchange current density on mercury, right? Like it does not react very quickly. Same reaction, but on these two different metals, it's much easier to get a lot of current on platinum than on mercury. So that's what you'll see in like the textbooks, sort of say.
And actually, it's part of the Butler-Volmer equation.
Yeah,
to your point about it, and that's where the Butler-Volmer equation has those exponential, which the Tafel again. I should kind of show this in my webinar. I actually do the derivation very quickly, but the Tafel equation from which you do a Tafel analysis and get the Tafel slope is just a rearrangement of the Butler-Volmer equation. It's actually just the Butler-Volmer equation.
That's right.
Solved for what, current or something?
Yeah,
so it's current. It's solved for potential, right?
They need to do a natural log.
Yeah, right. You solve for over potential because there's an exponential. That's all it is.
Yeah, that's right.
It's literally a rearrangement of the Butler.
Yeah.
And so this is why I say that there's that assumption. The Butler-Volmer equation is an expression to describe the kinetics, right? Whereas the Cottrell equation is to describe the diffusional processes. And it's like, there's no, just like you said, there's no electrochemical experiment that follows the Butler-Volmer equation perfectly. Like 100% of the time. So why would you expect your Tafel, analysis to be perfectly accurate? If it did, then everything would look like the Butler-Volmer equation, and it doesn't. Maybe over small potential ranges it does, or certain conditions. Okay, great. But that's the point, right? So the Butler-Volmer equation is where that comes from, and that is a purely kinetic equation.
Yeah.
So
I hope that answered your question. You're just like, what kind of information can you get from it? Engage massive rant about Tafel plot.
you hit a trigger point for me. You asked about the Tafel equation, and my eyes started twitching. So I had to go for it. I couldn't help it. I'm sorry.
That's good.
So Giannis has a question. Something about EIS. I haven't read it yet. I'm doing EIS to measure the ECSA of a metal electrode that has a positive ionic layer on top. Any idea of an equivalent circuit I can use for fitting? Positive ionic layer. So the question is whether that positive ionic layer is acting like a film and you have a substrate film kind of a situation, or it isn't. And so the question, well, part of the answer to your question would require me to see what your data looks like, which I obviously cannot do quite easily in this this particular venue here. But let's just say, for example, you had a Nyquist plot, for example, that looked like that. Very simply, you have two options. Hey, are you laughing at my semicircles?
No.
Yes, you should. They're terrible.
No, I'm just so used to like the elephant one where it's like semicircle.
Oh, the elephant. I didn't draw the elephant this time.
Yeah, I'm like, oh yeah, that's right. There's another one.
Yeah. It's like, oh, this is another
This
option.
is another option.
Because there's no inductive loops here.
My
See,
favorite.
you want somebody please ask a question about inductive loops so Alex's eye can twitch.
Please don't.
Tafel slopes are fine,
Al-
apparently. Oh, or
although
Lugan capillaries.
Lugan
Don't ask
capillaries.
about
That's
Lugan
another.
capillaries.
Yeah, you want to trigger Neil.
Yeah, please don't ask.
Tell him
Lugan
that Lugan
capillaries.
capillaries.
No,
Move them.
no, we're not talking about that. So this is
Okay.
this is one option. Oh gosh. You could have, for example, this. I'll just call this 1, I guess. I don't know. I could color code it too, but that's 1, and then this would be 2. So this is one option. So again, if you have 2 semicircles, you might have something like this. Another option for fitting this would be something like an embedded model. I'm going to try to draw this. I always forget which one. So it's a resistor
the
here,
embedded
and then
model.
it's this. And then there's a capacitor up here.
Oh yeah, and that goes all the way.
Okay.
Yeah.
So this is effectively an embedded. It's called the embedded model. So this is like this. I'm doing a great deal of skipping and making assumptions, and you're just going to have to bear with me because again, I'm trying to answer your question in fewer than webinar time, like hour-long discussion of what we're doing. In short, this is roughly speaking 1, which is the substrate. This is generally speaking 2, the film. So if your ionic layer, for example, acts like a film substrate where you have like your electrode here and you have your like film on the surface, your ionic layer, and you have some interaction between your substrate and your film, and then you have some other interaction between the film and the electrolyte, and this is where your this is too small, I know, I'm sorry. This is where your ECSA is because it's between the ionic layer, but you still have some electrochemical response between this interaction here. Then you'd be more focused on this one, this semicircle, for example, to get some capacitive information or whatever. But you might still have to account for this to get your fit right. Now, if you don't see that, there's something different, right? Then again, this is just one possibility for you because of just substrate film interactions. You tend to use this kind of call this. I should listen to you, right, and do the text box.
Oh,
I always try to write with this, and it's just a disaster.
that's all good.
This is called roughly an embedded model. So that's what you would call something like this. That's where you have a substrate and a film. And it depends whether you have, for example, the ability for your electrolyte to penetrate through to get to the bottom here, or this is not porous at all. So that would affect the ratio of these capacitors here, 1 and 2. These capacitors, they would vary. So there's a lot there. Again, I don't know the specifics about your system, so I can't answer it much more more detailed than that, but those are some possibilities for what you might have in this particular situation.
So how do you determine the electroactive surface area from EIS? Is it from the capacitance value?
I think I guess so, because the tricky thing is to be honest, the only one that I'm really like intimately familiar with is platinum.
Yeah,
with the
hydrogen.
Yeah, exactly. And so 210 microcoulombs per centimeter squared is the theoretical specific capacitance of the hydrogen absorption desorption reaction.
Yeah.
And so when you get a region
of
and so when you get a charge, you integrate under the current time curve there of the absorption or the desorption in your CV. And then coulombs divided by coulombs over area is area, right?
Yeah,
so you get area. If you have like other reactions have, I suppose, theoretical specific capacitances too. So I think that probably is what you would do. I've never done it, right? I haven't done it like myself. I've only done the platinum CV one. That's the most common one that's used really for ECSA. I think the only really way to get ECSA is to have some electrochemical reaction that you have a theoretical answer like that for. So whether it's the platinum desorption or whatever, hydrogen, or it's some other whatever, you have to determine its perfect theoretical specific capacitance, and then probably like you said, get the coulombs. Not coulombs. That's charge. So that's charge. That's not capacity. Yeah,
you're saying
so
once you figure out the specific capacitance, like capacitance per some unit area, and then when you figure out the capacitance of the species that you measure from EIS, then you could figure out the electroactive surface area.
Well, I think I was missing a variable here. So, for example, I always have to look this up because it's not like I have a PhD in this stuff.
Yeah.
I don't know that. So the charge is equal to the voltage times the capacitance. Q is CV.
Yeah.
I'm not talking about cyclical tamagram. Q charge equals C capacitance in farads times V volts voltage, right?
Okay.
So, for example, and I'm sort of shooting from the hip here because again, I haven't done this personally, but my best guess is you do your EIS, you get your circuit fit, you identify which of the capacitors is the one that you need. You get a capacitance value that's C.
Yeah.
In farads, right?
Yeah.
I'm assuming it's a C and not a CPE. Or just make some
Yeah,
assumptions, right?
Yeah.
Whatever voltage you did your impedance at, that's your V. Multiply those together, you get Q.
Okay.
And then you're dividing Q by 210 microcoulombs per, if that's the one, or whatever you have to know what your specific charge. It's not capacitance. It's like specific charge per area. I don't even know what the name for that is, right? 210. That's the one that everyone knows. 210 microcoulombs per centimeter squared. That's the one for the hydrogen adsorption on platinum. It's the specific charge capacity, or what's, I don't know what the name is.
Well,
it has a name.
you know what
I mean? 210 microcoulombs per. I'm messing. I said capacitance. I don't think that's specific.
And I know that works for hydrogen because hydrogen is small and electroactive and all that stuff. And I don't know if you have another molecule. I don't know if I'm complicating things, honestly. It's just I'm always curious, like, oh, I didn't know EIS is. So,
for example, CO stripping has a 420 microcoulombs. So every reaction, and I don't actually, I haven't done this calculation. That there's a way to calculate it. It's probably thermodynamics and stoichiometry of the reaction. Like there's a way to do this. I could probably figure it out. I haven't done it before. I don't know it intimately. And I'm like, so that's the specific charge per area of these reactions. What the heck is it? Has it have a name? Gamma, I guess. I'm trying to find the name for that quantity. You know what I mean? I don't know what the name of that quantity is.
Yeah. So, but in this case, the charge that you're measuring, like, could be electrolyte. You know,
right? I'm making assumptions with everything I just said. Like, here's my capacitance, and here's my voltage, and I get my charge, whatever. I'm making an assumption that is. Because you might get an ECSA that's like impossible, like it's more efficient than it should be, or something. Like there's some built-in assumptions here. The charge required to reduce a monolayer of protons. Yeah, it's just a specific charge or something. Charge. I don't know. And this is the case where probably whatever reaction you're doing to measure your ECSA, you'll have to look up what its thing is, right? What its value is. And then in theory, what we just described could work, but it might be, it's just tricky. Like, is there a lot of error built into that? Maybe, right?
Yeah. Tricky. And then I'm also curious about like the positive ionic layer, because metal electrodes by their very nature are negatively charged. So there may just naturally be a positive charge of ionic anything there. But hopefully
there's some assumptions built in here, and that's the best that I can give you. Because like I said, like I would say like 80-90% of papers you'll ever find in the literature that talk about ECSA, it's platinum hydrogen, that 210. That's it. Like that's the most popular one. It's used very, very frequently.
Oh yeah.
So all these other ones are probably possible, but tricky for sure. And I don't have any personal experience with it, so I'm just sort of assuming what might be the case there. So.
All right.
There's a lot of questions that were follow-ups from our answer to Nana, so I think we'll move on.
Oh yeah, and Kanav, thanks for stopping by. Good to. I've been in email contact with Kanav for a while, but he's been traveling. So
he's joined our some of our previous ones.
Yeah. That's a good seeing you, Kanav. Thanks for stopping by. As always, we're always trying to improve the setup a little bit. But let's look at.
Actually, we're just looking to change it constantly to keep you all on your toes. We don't know what we're doing. It's going to be different next week too.
Maybe, it's going to be different.
It's going to be at one of our houses again.
We have to figure something out.
We're keeping you on your toes. You don't know where we're going to be.
Yeah.
We'll be in your lab next week.
Yeah, that's And Ramachandra, if you have a question regarding EIS, please type it into the chat, and we will.
Actually,
try to
Ramachandra,
address it.
while he's
Did
here,
have a
there was a
he did have a
question that was
question
submitted.
earlier.
Yeah, why don't you answer this one?
Yeah,
Alex?
let me
Ramachandra,
see.
you had a question. I know it's small here. You can.
Yeah.
You had questions submitted before we started that I saved. So let's get to that now. Sorry if we waited. We weren't sure if you were here. So, but I'm glad if you're here, we'll answer your question that you had typed, before our event started.
Yeah. So we wrote that down, and the question is that you wrote: can we adjust the pH of the test solution using buffer solution, or does the test solution component have to be mixed in buffer solution to attain the desired pH? I'm kind of confused and want to know the concept behind it. So, well, buffer solutions, just very simply, not even electrochemistry, a buffer solution from general chemistry is a weak acid or a weak base. So let's say it's a weak acid. It's a weak acid plus its conjugate base in the form of a salt. So, for example, you can make a buffer of acetic acid plus the conjugate base in the form of a salt, so sodium acetate, and a mixture of those two would form a buffer. And buffers are really just things that kind of maintain a pH. The pH doesn't change very quickly or rapidly when other things enter the system. So it's just supposed to maintain a stable pH. So you can, if you have an electrochemical test solution and you add a buffer solution, you can affect the pH. That can happen. And so let me make sure I understand the question. So you might, and again, most of these are chemical system dependent. So you might be able to adjust the pH of the test solution by using a buffer solution. You could add a buffer solution to adjust the pH. And does the test solution component have to be mixed with the buffer to attain the desired pH? Kind of yes and no. Sometimes it depends. Like if you want to, I guess there's a lot of possible ideas regarding this. So for example, if you're doing an electrochemical reaction that's pH dependent and you want to maintain the pH, having a buffer is good. Or if you're doing an acid catalyzed reaction or an OH basic catalyzed reaction, and you want to, so as the electrochemistry is happening, the pH might be changing. So you might want to add a buffer so that the pH doesn't change. It still might change. We have the idea and concepts behind buffer solutions and maintaining pH, but that it just means that it resists. Really, it means it resists changes in the pH. But it doesn't mean that the pH can't change. Like I might have an acetic acid buffer solution, but man, if I dump a bunch of like sulfuric acid in it, it's like you better believe the pH is going to change. So hopefully this provides a little bit of information behind the concept of pH and buffer and just test solutions and electrochemistry.
Yeah, and Chris made the comment too, which is true. It would depend if the buffer is electrochemically active or can participate in reactions.
Yeah.
So
yeah, that's also true.
like acetic acid can be oxidized. Like if you have a certain kind of electrode, so your buffer might be hurting you by providing extra reactive species, and that can be a problem too.
Yeah, that is true.
So Ramachandra added some. I had the pH adjusted analyzed that was tested in cyclic voltammetry and EIS simultaneously. After the process, I found the pH was dropping. Yeah, I mean, there's obviously some reaction happening if the pH is dropping for sure. The interesting thing in some sense is that electrochemically, with a normal, I'd say, typical kind of small electrode, even when you're getting what looks like a lot of current, if you do the math out, it's a change in like the amount of molar you're changing is really small. So it's hard to believe that doing some electrochemistry would dramatically change the pH, even if if you're in acidic solution and you're producing hydroxide at your electrode, like whatever, right?
Yeah.
You're technically neutralizing some of it, but it's like the rate at which that happens compared to the bulk solution is really not in the favor of changing pH. So something else might be going on if you're seeing some crazy thing like that, which might not be electrochemical. There might be some chemical temperature. I don't know. Something strange is happening, I think, is my guess.
Yeah.
That might not have anything. And this is a live stream about asking us about electrochemistry, not chemistry. So it's not electrochemistry, and I don't know. I'm just teasing.
No,
Yeah, no, I mean, honestly, yeah, to have the pH dropping like that a lot, honestly, it probably has less to do with electrochemistry. There's probably some chemical thing happening.
One thing to keep in mind, like, we don't know what your system is. One thing to keep in mind is if it's a slightly basic solution or basic system, and you aren't that system basic.
You basic system.
There's a chance, like, if you weren't degassing the solution, CO2 can dissolve in your electrochemical cell.
That's acidifying it,
and it's acidifying your solution if it's aqueous.
Yeah.
So that's one thing. How much is the pH dropping is another question. Like, if it's like if it was a pretty basic solution, I mean, we're talking like Starbucks. Like, I buy Starbucks.
I like Hey, you're calling me basic? I am basic.
No.
Yeah. Like, buy like pumpkins. Oh, I love pumpkin spice lattes.
We need
I'm very basic.
We need like a pH scale that also corresponds to like
like
basic.
Like pH 14 is like pumpkin spice latte on the 1st of November.
Yeah, that's right.
Like basic, like that's me. I love I don't care. I have no shame whatsoever. I don't care. I'll admit it.
But if it's just like, I like to play like Settlers of Catan, which is a fun game.
That is a pretty fun game.
That is a fun game. But
I used to play that in college. Oh, that's a fun game.
Is
that basic or is that not basic?
I don't know if that's basic or
that's
not.
Like neutral. That's pH 7.
This is a question for the audience. First off, do you know what we're even talking about? But what would be the equivalent pH scale to the other basic scale?
Yeah.
But I'm saying, let's say you had a pH of 8. I'm just saying pH of 8. It wouldn't take that long for CO2. Like, if you bubbled CO2, it could go to like 6 or 5 if there's nothing else. Again, if you don't have a buffer, it could actually go pretty low if there's nothing buffering.
What's the equilibrium for like carbonic acid? Is it like 4 or something? Like, if you were to bubble CO2 in water by itself, doing nothing else, eventually it will equilibrate. It's not like really acidic, but it's like 3 or 4 or 2. It's in that range. It's something like that.
Yeah.
So the point is that it will change like over time. And conversely, if you bubbled CO2 or you have acidic and then you just let it alone for a while, eventually it will diffuse out.
Yeah.
So it's like a soda, right? If you keep a soda open, it's bubbled CO2. Like, eventually the bubbles will leave and it will become less acidic.
Yeah. So we're also assuming you're at atmospheric pressure. If you have a pressurized electrochemical cell, because you're pressurizing CO2, then you're gonna have more carbonic acid. You're gonna have more. You're gonna have a lower pH. So that's another thing, Ramachandra, too.
Also, Chris says breaking down organic molecules can do very strange things to your system. Ramachandra agrees. Yeah. So that I mean, I discounted that to a certain degree electrochemically, because the rate at which molecular changes happen on a small disc electrode is pretty small. But that isn't to say that nothing is happening. Maybe there is causing some reaction that's causing a shift, and like you said, the strange things can happen. I suppose, can happen. So I also wanted to. Chris was following up some of previous one we talked about. I just wanted to clarify one little thing. You basically was with respect to the copper and iron plating. Chris was saying, basically references for the various parameters and application tables of potential. So I was just using whatever that reference is. I'm just on some page. It's like Chem Libra texts. It's just a standard potentials page.
We can put the link in the.
I don't even. Yeah, I'll put. It's just. I don't even know where I literally just Googled.
Oh, you just
found this. It's just. Here's the list of standard potential. I don't know if that's exactly what you're talking about, but the point that you made that I wanted to comment on, Chris, was, we were talking about, pick your potential. You're going to plate one thing. You're not going to plate another. And you made the comparison to, is it acting as a diode at the surface in that case? Just to be clear, what you're sort of referring to is like, well, if I'm doing, I don't know, CV, and is it going one direction but not the other? Can I polarize a reaction one way or not the other? Diode is like that's an electrical term that allows current to pass in one direction only. That's just not the right. I wouldn't think about it that way when we talk about something that you would perceive as a diode in electrochemistry. You would think about it as like an irreversible reaction.
Yeah.
And certainly some reactions in electrochemistry are irreversible, which is like diode in some sense. It just means that you can oxidize it, but you can't reduce it, or vice versa. Right. It's like sometimes it's because it's like when you reduce something, it makes a solid, it plates or whatever, and then it's like intrinsically insulating. Like it's not even conductive at that point. There's a lot of battery electrodes that behave this way. Like once you've charged them too many times, they form this species that isn't electrically active or conductive, and so it doesn't work anymore. So it's like irreversible. So it's like a diode, but you wouldn't call diode in this context. It's just a terminology thing. That's all I was going to say.
Yeah. Where are we at right now?
Yeah, making sure we didn't miss anything. I don't think. Okay, Kanav likes our setup. That's very important.
Yes.
And next stream is going to be the James Corden car stream. That's right. I'll break out some guitar and we'll start singing and driving and for our live stream. That's what's going to happen.
Let's see. Giannis was telling us that Giannis only has a single semi loop that's slightly flattened, so I'm using a CPE instead of a pure capacitor.
Yeah.
And my ion layer is a cation that I'm chemically immobilizing. Okay, so it's immobilized on the surface. I mean, yeah, metals have a negative charge, and it's pretty hard to change the charge on a metal to being not negative, and then to have a positive ion on the surface is good. Okay, all right, so that's good to know. And Giannis did mention another method for determining the ECSA is to make CV's different scan rates, plotting the difference in J over 2 for scan rate. The slope. So that's a way of getting the capacitance. I'm on the fence about getting the electrochemically active surface area.
Yeah, that's a way to get. I think that is I think the point though is that once you get the capacitance, if you know that specific capacitance value, you're getting the ECSA. Because what you're describing is a way, for example, that people test supercapacitors, right? You do different scan rates, and it's right. It's the okay, whether it's so you're talking about if you just get the current, for example, at different scan rates, the capacitance is it's the sweep rate times the current. I always screw that one up too.
Which one?
The equation to get like
double layer capacitance.
Yeah. But it's
the current. The current is equal to the capacitance times the scan rate.
Capacitance times scan rate. Right. So the capacitance is the current over the scan rate. Is that right? Or did I do backwards?
Current over the scan rate. That's correct.
Okay.
That should get you.
Yeah, that should get you the capacity.
Fair.
Yeah. So Giannis, in short, that is probably a way, another method to sort of, in a DC
the DC
method to extract out the capacitance, and then you could, in theory, get the ECSE that way.
Yeah. Chris is saying that it's absolutely keeping the topics and the chat in sync is definitely fun. And
yes, not always easy. Something goes by. We talked about it a while ago, and then it's like, oh right, we were talking about that. Yeah. Okay, so I think this is a good chance to get to some of the other questions we had seated.
Yes.
If there are any other questions, feel free
please.
to keep asking. But we had a few other questions that were from before. Again, let's see, which one did you want to get to?
I'm actually gonna remove one that we already answered.
Oh, right.
So we answered Ramachandra, so I'm gonna remove that one from the list. We could do Pete.
Yeah, why don't
Navudi's.
you answer Pete's, and then I'll get to, or why don't I? Well, yeah, go ahead.
Oh, okay.
Go ahead.
Yeah, sure.
Yeah.
So this is on the last live stream. Pete Navudi couldn't make it, but he had this question, which is effects of solvation. He wants to know a little bit about the effects of solvation and ligands affect the different ones that have a stretching duck neck, single electron transfer, and why there's like a 59 millivolt difference, diffusion cap. Let's see more on one layer. So a lot of this has to do with the question, the way I've read it, is how do ligands and solvation shells change and affect a cyclic voltammogram? Is basically what I'm hearing. When you have some kind of metal centered complex and you are trying to and you have different ligands on it, how do those ligands affect the electrochemistry? What do they do, right? Because there's a whole field of inorganic chemists who are doing just that. They're making these complexes with all of these different ligands attached to it, and they all give very interesting different electrochemistry. Some is chemical steps and things like that. And in specific, he's also asking about this stretching duck neck for single electron transfers and this difference in 59 millivolts. So actually, to demonstrate this, I'm going to try something. Let me see if I can share my screen. So hopefully you can see this. This is kind of a beta version of our software. Hopefully you can see that. But basically,
it's not.
Oh, is it not showing up?
Hang on. There we go.
There we go.
It wasn't
Okay.
maximized. Got it.
All good. So we have a software that can do. We're developing it, and it's working reasonably well. But basically, we can simulate a cyclic voltammogram. And what I'd like to show, Pete, is that if I have I'm basically putting in the parameters of a cyclic voltammetry experiment, and I have a 1 electron transfer mechanism. So there are really two things, in my opinion at least, regarding, and I'll talk a little bit about it, but it changes this part, which is the heterogeneous rate constant. So let me actually simulate this. So you get a nice, like, perfect looking duck when you do this. But if, say, the ligands, whenever an electron transfer occurs, that the ligands, the solvent, the solvation sphere around it reorients. And then when oxidize it and then reduce it, you have the reverse reaction, then it has to go back to that original configuration. That's all part of it. And what that can do is it can change this heterogeneous rate constant. That's one thing it can do. So instead of having it be 10, this is still actually pretty fast. You don't notice much of a difference in the voltammogram. But if I start to go to slower and slower heterogeneous rate constants, you'll start to notice that the difference between these two peaks starts to increase. If I increase it again, I know I'm going like an order of magnitude. It doesn't always shift this much, but this is what he's saying when he's talking about this kind of long duck neck. When you do something like this, yes, you keep increasing this, you'll notice it separates. And that's because sometimes when you have an inorganic complex that's got these big ligands, and when you transfer an electron, it takes a lot of time for them to orient and reorient themselves. And then when you change them back, it also takes a lot of time. And this is really just it. It's the time. This separation, this elongation of the duck is a representation of that slow electron transfer because of the reorientation of the ligands and that solvation energy, a solvation shell around the molecules. Another thing that can happen is changing the ligands in the solvation shell can also affect alpha, which is the transfer coefficient. Now, the alpha transfer coefficient just means there's a symmetric energy barrier between reduction and oxidation for a molecule. But sometimes maybe the ligands make it so that the reduction is more preferred or the oxidation is more preferred. And you start to get things where it's no longer 0.5, which represents a like 0.8. And then if you have this slow rate constant, it also changes it so that one side is more favored than the other. If I go to like 0.2, I'll notice the opposite. This one is way more favored of a process. So this is hopefully Pete Venuti, this hopefully this is helpful in kind of understanding. I'm just going to stop sharing, but I'm also going to hopefully share a little bit of just you know, just for a little bit of clarity. Like when I talk about something, let's say you have like cobalt, right? When I talk about ligands, I'm talking about like these. I'm talking about like these two axial ligands, and I can't really draw the whole, like, I think this is like out of the plane, and this is like also out of the plane, and this is like in plane or something like that. So you have you have these ligands here, right? For these complexes, and what happens when these change? And then there's like there's solvent molecules around it. You know, there are these solvent molecules.
It looks like you're writing LOL a bunch of
LOL,
times.
LOL, LOL. So
It's
basically,
the cobalt LOL.
it's the cobalt LOL. So basically, like, yeah, when this goes from like 2+ to 3+, like all this stuff has to move around a little bit, and that's what I mean. Like difference in ligands, difference in the solvation sphere that's around it, and so just kind of hopefully this is helpful. Let me stop sharing. Okay, so yeah, so hopefully Pete Venuti, this is helpful.
So
I think we got some new questions.
yeah, there's
in the
there's
meantime.
one new one. I wanted to try to touch on a couple of things before we do. I do want to. I think I'll
Yeah.
try to touch it. There was a brief thing from last week. I just wanted to make a clarification on fuel cells. Someone asked a question about, can I use air or oxygen? I just wanted to make a quick note about, you can run a fuel cell with air and you can run a fuel cell with oxygen, and the only difference is that one of them will give you better results, basically. So like I think the question was something along the lines of like, well, if I'm making a car, it's preferable, like if I have a fuel cell car, I have to have a tank of hydrogen, right? Because hydrogen is the fuel on one side and then oxygen is the fuel on the other side. Well, it would be preferable if I didn't have to lug around an oxygen and a hydrogen tank, just a hydrogen tank, and I could just suck in air. You can do that. You just get worse performance because air is 80% nitrogen and 20% hydrogen, roughly. So of every chunk of air that I draw in to my fuel cell, I have 80% of it is inert and not helping me. So that's it. And people do this in the literature. They do like power curves or polarization curves of a fuel cell in air and in oxygen. And oxygen's better because it's pure fuel, and in air you get a little less good results. And so yeah, you certainly can. I just wanted to make that note that you can do that, and really the main difference is how good your results look. And then there's other things, like for example, if you're doing just pure air, let's say you're in a city and someone's smoking a cigarette near your car, there's going to be some carbon monoxide.
Yeah, that's right.
It might suck in carbon monoxide as part of your air, right? Contaminants. If you do air, on your side of your fuel cell, you might get contaminants in there that can deactivate your catalyst. And so that could be bad. So that's one reason that you wouldn't want to use it, in addition to the fact that its performance will be a little bit worse. That's just one of those kinds of things about it. But as far as whether it would affect the atmospheric O2 concentration, not even a little bit. Not even the slightest, tiniest noticeable measured amount. Absolutely not. Every car could suddenly be a fuel cell car and we would not run out of oxygen to breathe. Don't worry about that. Okay. There's a couple others. Was there a new question?
Yeah,
We could
I
probably
think
get to a
that's
new
good.
question.
One thing I would like Chris to comment on, because I forgot, like, what were we talking about that he was interested in characterizing? Because electrowinning just sounds like your electrochemistry experiment worked.
I'm all about electrowinning.
An elution system. So
don't be an electro loser.
Yeah, don't be an electro loser. So yeah, Chris, we're more than happy to talk about any of these types of topics. I just wish I knew more about what.
I'm not happy to talk about them because I don't know what it is.
Yeah, I guess I don't know, but we're interested
Exactly
in
what you're
learning.
talking about. Yeah.
Learn all kinds of these kind of new things.
Yeah.
But Shadab has a question. which I think we can look at. How can we identify our system is double layer from looking at a Nyquist plot? Also, I'm curious why imaginary impedance of Nyquist plot is always negative. So I'm thinking either one of us.
So the whether well, I don't know if the answer to your first question is if we can. I think that usually from the context of the impedance data and the context of our system, we can know whether the capacitance that we are observing as part of a semicircle or something like that is the double layer capacitance, or something of that nature. So by itself, if I just am given a Nyquist plot with no other context, it's like I might guess that that's double layer capacitance. But generally speaking, part of the reason you know that is because it's just always there. So in some sense, the answer to your question is because if you have a liquid electrochemical system, there is double layer capacitance, whether or not you like it. Right.
Yeah.
And so if you have a capacitance show up in your Nyquist plot, it's probably double layer capacitance. Like it's almost, there's almost no other thing it could be. Now there might be exceptions to that in very, or it's a different process that looks like capacitance, but it's actually like a Warburg thing. Like there's other explanations, but it's like if you see capacitance, most probably that's what it is. So in some ways, the answer to your question is like, because it is, and I know that's not very satisfying, but that's sort of just the reality.
There's another thing too.
Oh yeah.
Which is double layer capacitance typically. So you may be using electrodes of varying sizes, but generally people are doing stuff with like, I don't know, I'm going to say between like 1 to 5 millimeters at best.
Yeah.
The electrical double layer of those types of systems is in the microfarad range. So, I think like a typical value for the double layer capacitance is 25 microfarads, which is massive. It's like, that if I'm doing the EIS and I look at a Nyquist plot and I get my fitting and my capacitance value is like 25 or 30 microfarads, it's the double layer capacitance because it's huge. So that's another thing. It's the capacitance value, because there are other things that have lower or higher capacitance values, but I know the microamp is typically microfarad.
Yeah.
Right?
Actually, that's a good point to also note why perhaps in some general sense, supercapacitors are an area of study for electrochemistry, because that's a big capacitance.
It's a big capacitance. And
electrochemistry gives you that whether you like it or not. So if I like it, I design a supercapacitor to take advantage of that, right? Like that's a stored energy, right? And a capacitor is a way to deliver stored energy. So supercapacitors are a very, well-studied field. That's one of the reasons why. And then the second part of your question, why is imaginary impedance negative? Because of math.
Yeah.
Because of math. Again, I'll sort of plug my webinars, but in my webinars, EIS webinar series, I kind of show the math of it. Basically, I'll just share a screen. I can do a little bit. I won't bore you with tons of math unless you're a math nerd like I am. I really do enjoy math, but is it okay? It's sharing. Oh, can you get rid of the question?
Yep, I have the question.
So briefly, the equation for the impedance of a capacitor is 1 over J omega C. J is the imaginary number. We don't use I just because I is current usually. So just to right, this is the square root of -1. Effectively, what we have here, this is capacitor. So the impedance of a capacitor is this. So what we do is we bring J to the numerator, right? So it's minus J over omega C. So there's a minus sign here, right? So there's a two-part answer to your question. Number one is that fundamentally, mathematically, the impedance of a capacitor is just, it's negative, right? This is a constant. This is frequency. So that's always a positive number. And so it's just negative. And it's an imaginary, I'm skipping a step. It's a negative number. Okay. So first of all, the impedance of a capacitor is a negative it's like it's negative. It happens to be. Okay. The second thing is that, just like we said, there's always double layer capacitance or whatever. Almost all processes in electrochemistry, particularly when you're doing impedance and you're observing the gamut of things happening at your electrode, they are fundamentally capacitive and resistive, but capacitance is like always present. That means I always have some capacitance and I always have some of this going on, which gives me a negative number. Now, the other thing is that this is J. So if you think about complex numbers, right, I have A plus B I, that's the typical, or BJ, whatever you're calling the imaginary number, right? This is the real component, and this is the imaginary component. The impedance of a capacitor is 100% imaginary and 0% real. It's only imaginary, right? Similarly, the impedance is Z real plus Z imaginary. So 100% of the imaginary most often comes from capacitive effects, which, as I just showed you, are negative. That is why Z imaginary is almost always negative.
Yep.
Ta-da. That's
Ta-da.
it. It's just math.
Yeah.
So
and the
that's it. It's
impedance
really just math.
of an inductor is positive.
Yeah, and if you have an inductive loop, it's really cool.
Yeah.
You should ask questions. Yeah, see, Chris says compared to Z inductor.
Yeah.
See, he's triggering you now.
Yeah, he's triggering.
That's
me
right.
there.
Inductors are the exact opposite. Inductors are 100% positive. They just don't show up very often, except in weird, corrosion kinds of things.
Yeah. And so Shadab, in the Nyquist plot, we have the first quadrant of the graph is real impedance on the x-axis and then negative imaginary. If we plotted it where imaginary was positive, all of our graphs would show up in the fourth quadrant.
Yeah, and they'd be upside down.
They'd be upside down,
and
basically.
It's just nobody wants to see upside down semicircles.
People like to look at them.
It's really
in the first
just
quadrant.
Exactly. It's just a convenience thing. We just like to see semicircles up, right side up or whatever.
Yeah.
So that's the only reason. That's really the only reason we plot Z. Some purists will plot it down, but very few.
Yeah.
So
yeah.
I want to get to this shunt thing.
Yeah.
So there was this. There were some questions on our YouTube channel from our friend Tarek, who was, and then I think you talked last week also about this whole shunts and EIS and high frequency.
Yeah.
And so I just wanted to touch. What's that?
And we talked about it more in between.
Yeah. So
it's interesting.
So in short, we have a video on our YouTube channel. It's from a webinar I did where I talked about a shunt, a reference electrode shunt, and how it works. I'm not going to cover that now. That's more in depth than I want to cover at this moment in this live stream. So if you don't know how a shunt works, can you put the link to the video in the chat if you wanted to know how a shunt, my little 10-minute or session about how a shunt works. I just wanted to go through some of this synopsis here because I think it's an interesting thing. And so effectively when you have a shunt and you have a reference electrode present for impedance. Now, a reference electrode itself, sorry, I'm not sharing. I need to share the screen. Okay. So a reference electrode itself, is it sharing? I didn't even look.
Yes, it's sharing.
Okay.
It should be.
So I have a reference electrode, right? I have a frit here at the bottom. I have a silver wire with some silver chloride on it or something like that. This is my reference electrode, right? And it's a glass tube. This is with electrolyte inside and a frit. So often people will say a reference electrode has somewhere between 7 to 10 picofarads of capacitance by itself. Now, this is somewhat of a theory or a guess, I guess, if you want to call it that. But effectively, when the capacitance of my reference electrode is intrinsically whatever this is, our best sort of guess about what that is it's through the glass, right? You have effectively a capacitor through this. This is like a glass tube, right? Mm-hmm. And I have electrolyte in here. Let's say this is KCl, and I have my whatever sulfuric, whatever H2O, H2SO4. I can write.
Yeah.
Yeah, my electrolyte is over here. This is my bulk solution, and this is my fill solution. So there's going to be some capacitance through here. Okay, so and actually I won't do the math out now, even though Chris, you said more math is more better. I agree,
Yeah.
but I will spare you more math, less better right now. There's a quick you can do a really kind of rough quick calculation of the capacitance is the dielectric constant times the surface area divided by the distance separation, and the dielectric is of glass, which isn't a very good dielectric, but it does have a dielectric constant. Effectively, you get something like 10 picofarads. It's kind of remarkable, actually. It's cool.
Yeah.
So that kind of bears out that this is where that capacitance occurs. Now, how as it relates to a shunt, when you're doing your experiments, this is my reference. That's an alligator clip. Okay. When I have a shunt, I have no drawing abilities. Just bear with me. Okay. Here's my reference electrode in solution. So this is one pathway, right? This is my reference electrode. And I have another pathway that has a capacitor and then a piece of platinum or something like that. Now, if this is not here, forget about this right now. I'm just talking about the reference electrode itself. Okay, let's blow this up. That means that when my potentiostat is measuring the reference electrode, the circuit is effectively from the reference line. Thinking about this over here, I have a resistance. This is the AG wire, the AGCL, basically.
Yeah, the frit.
Right. Well, no, not the frit.
Oh, no,
this is
not
not
the
the
frit.
frit.
This is not the
right.
frit.
Then, basically, where and this is a bit complicated, but where it's sensing is right here, just outside of this frit. I have my working electrode or whatever. The sensing point is actually just outside the frit. You'll have to take my word for it. Basically, that's where it is. So I have to get from the top of this pin, this clip, through this silver wire to this point here. I have two options. I can go through the frit, or I can go directly outside the glass. Those are two options. They're parallel paths, right? So that's how I can get from point A to point B. From here to here, I can either go through the frit or I can go through this capacitor. It's going to follow the path of least resistance, always. So just like I've talked about in the past, one of these is bigger than the other. It depends on the frequency. With 7 to 10 picofarads, only at the highest frequencies is this going to be smaller than the impedance of my frit. My frit might be, at worst, I'll just go worst case scenario, 10 kilo ohms. Okay, something like that. That's high. Maybe it's 1 kilo ohm. Okay, but that's the impedance of this frit to get through here, this from the silver wire here. So at really high frequencies, this right here is actually less. And so I'm effectively trying to sense potential through glass and a capacitor around glass. As best as we sort of can tell through our discussions with our electrical engineer and chemically, electrochemically, everything, this is what accounts for those artifacts at high frequency. It's because your reference electrode is fundamentally incapable of measuring through the frit at the best, if you will, path. And this capacitance through the glass is interfering. And that's where you're getting those artifacts. And so when you apply your shunt, what you're trying to do with this capacitor here is you want to pick a capacitor value that's just above the capacitance of the glass in the reference electrode, because that will effectively cut out that as a pathway. Okay. And there's a lot more we could probably say about this. It's pretty technical. The one thing that I wanted to say as a takeaway, okay, is that this capacitance of your reference electrode is dependent on surface area. Now, the dielectric constant, that's glass. The distance is the thickness of this glass. That's that D. Those you can't change that. But this surface area, that is the surface area along the glass tube. So what this means practically is that if you have high frequency artifacts and you're using a reference electrode, One way that might work, I haven't tried this, but in theory, this should work, I think. The depth of your reference electrode in your solution might be a problem. So if I have my reference electrode in solution and the liquid is here, the surface area that's contributing to this capacitance is directly related to how far down my reference electrode is. So if instead I raise up the reference electrode and all I really need is the tip, I mean, you'll have to make sure you have a good signal, right? But effectively, if I had just the bottom part touching, the surface area of the glass tube with my electrolyte is really quite small here. That means my surface area here is low, which means my capacitance is low, which means this capacitor is low, and it will play, in theory, it should play less of a role, and I might be able to reduce or eliminate some of those artifacts. And that would actually mean I wouldn't necessarily need a shunt at all, depending on how high of a frequency I'm going. And part of that reason is that, related to this other discussion I think that Tarek was bringing up and you talked about last week, is that and this circuit is wrong. I drew it wrong like a dummy. It's this, and then there's another one of these. And I'm getting overly technical here.
No, it's all good.
This is the AG wire. This is the frit. And this is the glass. So in other words, I'm going either in this direction or in this direction. This one's bad. This one's preferred. Okay. So the point is, raise your reference electrode out of the solution a little. You might get rid of some of those. And the reason for that is that using a shunt can help clarify artifacts. But the problem is that you are using this platinum wire as your pseudo reference. So it does call into question what potential I'm at when the shunt is being used by the reference line. Whereas even if there are artifacts at high frequency, but I'm just using a reference electrode, I'm still going through the AG wire no matter what. So errors in high frequency are still with respect to the potential that I want. What's more important? That might depend on your situation, right? Does it matter that I get my artifacts gone, but the exact potential I'm at is who knows because the reference is not the same? Or do I just want to make sure I'm always at the right potential, even if I have a little bit of artifacts? Those two things are not exactly the same. And whether or not one is more important to you is probably up to you. So I tried to do that quickly. I know I could probably, we talked about this for hours. And I just wanted to comment on that. And again, the main takeaway, if you heard nothing about what I just rambled on and tried to draw terribly at, if you have high frequency artifacts, try to dip your reference electrode as little in solution as possible. I think that might help. So,
we talked about this for a while, just wrapping our head around the idea of glass capacitance causing issues. But
it's really funky and interesting.
It is funky and interesting.
But I think it's a cool thing to understand more, as even by us, I put out the video, I'm talking about the shunts, and I didn't understand any of this when I made that video. I almost wish I had, right? So it's kind of fun to learn about.
Continues to learn new things.
I
think we have a little bit more time. I don't know how you're feeling.
I'm okay. I'm gonna pass out in 3 minutes, but no.
We have a question from Haifa in the chat. Could you describe the physical mean of the modulus of impedance on the Bode plot? I actually don't know what Haifa means by modulus of impedance. Like
I'm trying to figure that out too. Exactly what.
Is it a point in a Bode plot?
I mean, I think you mean like the impedance magnitude. I think that's just another term for the impedance
for magnitude.
I think so. The modulus of that's one of those terms that's not used as frequently, and I think it's just another name for the impedance magnitude. So it's like there's like a Bode plot. It contains the phase angle.
And
then impedance
magnitude.
Z mag, or usually absolute value of Z. I just want to make sure that's what you mean. I think you mean the impedance magnitude.
And please let us know.
So I'll proceed as if that's what that's what you mean. And if it isn't, please correct me. What's the physical meaning of the impedance magnitude? I'm trying to think of a way to describe this. So the first answer is, if you're mathematically inclined, this is the mathematical answer. It is the
It's the vector sum.
it's the vector sum of the component impedances of real and imaginary. It is the hypotenuse on polar coordinates of the Nyquist plot. So if you have a Nyquist plot, it is the distance from the origin to any point. That's what it is mathematically and visually. Like physically, what it is the.
If you don't mind, I can share just a quick.
Yeah, go
I
ahead.
like to, like, in the EIS video that I made with Neil's help, I make this. But like the way I thought of it is just like, I think it was like you have Z real. I think it was here, and then you have like Z or negative Z imaginary, and then. And let's just say we have this, and so the magnitude that you would show up on the Bode plot is this vector sum of both the x and y components, and this is supposed to be a dashed line.
Yeah,
and then this is the phase angle.
Exactly.
So that's a way to kind of think about.
That's how you connect Bode and Nyquist plots.
That's how you connect Bode.
The Bode plot stuff appears on the Nyquist plot.
Yeah,
that's where it is. As far as physically, what it is, I don't know if this is the right explanation or the right words to use. I would try to loosely describe it as the aggregate impedance of the system at that frequency. So in a similar fashion to how the current is actually an aggregate current of all processes that are happening, oxidations and reductions and capacitances and whatever. So when you have 10 milliamps, you see that's 10 milliamps total of whatever processes are occurring, positive and negative, and they add up to 10. So most of what we do in impedance is we're deconvoluting, and we're getting the resistances and the capacitances, and we have the Z real, which is like the real component, or the in phase resistive in many ways component of the impedance. The Z imaginary is like the out of phase, often capacitive or inductive portions of the impedance. The Z magnitude is, again, roughly speaking, the aggregate
vector sum.
I
use vector sum.
That's very mathematical. I'm trying to describe it in like real phenomenon. You know what I mean? It's not wrong to say it's the vector sum. It's just it's like physically your electrochemical system has some impedance associated, which is the resistance to the flow of an AC current, an AC signal. The like bare bones raw impedance of that signal at that frequency, that's what the modulus impedance is. That's what the impedance like. That's what literally what the potentiostat's measuring.
Yeah.
You give it, you send a sinusoidal AC potential, and it measures a current back, and the ratio of those is the impedance. That's it. Like it's right. It's physically the actual like impedance measured at that frequency.
Yeah, that's right.
Overall, which is an aggregate of a lot of stuff, but right. Yeah.
So that's true, because it is just based on the magnitude.
Yeah.
Like the magnitude is that ratio of one sine wave and another sine wave.
Yeah, it's
let's see. Well, guys, thanks for all the answer. I was really talking about modulus Z mod. What is Z mod? What
is Z mod?
I'm not so sure what Z mod. We're not so sure what Z mod is.
Is it a different company that
yeah, or if you have like a link to like a Wikipedia or something.
Well, I think this is this like a Gamry thing? Did they have I'm trying to see if I can find
yeah, I'm gonna also try to look impedance. Okay, impedance modulus definition. From a general point of view, the impedance modulus represents the voltage amplitude for a current amplitude of value unit flowing through a circuit. That's just when I do a Google search of modulus.
I'm not see modulus.
Yeah, let's see. Any
I'm not certain this isn't used interchangeably with Z magnitude, which is why I launched into that long explanation about it.
let's see. Chris says frequency dependent impedance.
Oh, are you talking about just Z itself? Is that, I mean, so again, Z.
And Haifa is using gamma,
Yeah,
which is why there's
assume.
a problem, right?
Again, this is there's a definitional thing here. So just again, briefly with the definition and like the mathematics of this.
So I mean, it's like
Z is equal to okay. E is equal to IZ, generally speaking. So Z is equal to E over I. And these are time-based curves, which is equal to, let's say, E naught sine of omega t divided by I naught sine of omega t minus a phase angle. Okay, so this is like the most general form of impedance. Basically, this is impedance as a function of time. Is this what people are calling Z modulus? Because again, when I look, even when I do like a quick search, like an image search or in the literature search for Z modulus, you'll see stuff like Nyquist. I see Bode plots, and they're calling it Z mod. I'm pretty sure they just mean the impedance magnitude. So I think these might be interchangeable terminology, or if it means this is like the time dependent impedance. So this E naught over I naught, that is the Z magnitude, which is what I was assuming is meant by Z mod. But otherwise, it might be the more general form of the impedance, which is not frequency dependent. It's the function of frequency or time, basically. So again, I guess to a certain extent here, I'm not positive because I don't know 100% what the context is or what. Yeah, I don't work for Camry, so yeah. I don't know 100% what they are calling Z mod, what it is, you know what I mean? Like,
yeah,
I don't know. I
even did just
this is the formula for Z mod calculation. Okay, the one that I showed with the time based or whatever. So, okay, so
do you have that?
Yeah, it's Z is equal to E over I, and then that's E sine whatever. What's the physical meaning? I mean, that is the mathematical. Here's what I'll do for you, which is, I mean, without going down another rabbit hole that perhaps isn't exactly answering your question. To a certain extent, the answer. Nope, that's not what I wanted. Wait, yeah, this is where I wanted. So a lot of this is mathematical because the basis for that impedance stuff, I laid it out in this article that I just put into the chat. That's the mathematical theory of impedance. That breaks down it answers a question about why is Z imaginary and negative, and it answers the question of how you get how you break down mathematically
Mhm.
all of that. So I don't call it, again, I don't use the term Z modulus or Z mod, but hopefully you can correlate, maybe if you see that, what I'm talking about there. Some of those equations, maybe they'll make sense. And I'm sorry if I can't give you better answers than that, but yeah, some of this is a terminology thing. I don't 100% know what all of our competitors are using. I know some for the, obviously I have some exposure to our competitors' software and their different kinds of information there, but I don't 100% know. So I can't really dig into it more than that.
Yeah. It's like, what is it? This is not exactly guaranteed the problem.
Yeah, it really
Wait,
differs from Z real of the system. As I see, it's just on the representation of full impedance of the system taking into account.
Then it would be the Z magnitude.
I mean, I think that when we're talking about whether it's Z magnitude or it's like Z, again, whether that's Z modulus, I just call it Z, like if that's what it is, real and imaginary. We're just sort of talking about,
it's the representation of the same thing.
Well, it's like we're talking about one step in the simplification process. Like Z as a function of time is, or as a function of, Z as a function of time is that equation I showed you, which is E naught sine of omega t over I naught sine of omega t. Like that's just the general expression for impedance as a time-based function. So that is not, that is for all frequencies. That's not a frequency-specific equation. So that is not even what's really used. That expression itself is not used by analysis. That is what's used to get to the analysis, because you simplify that expression and you get a per frequency kind of thing. That's where Z mag comes out as a function of frequency and stuff like that. I guess it's like you're asking about the physical representation of a mathematical formula. That's an odd. I'm not. Yeah, I guess I don't know better how to answer that, so I'll leave it there.
Yeah.
But
sorry. Hopefully, this is kind of helpful in some way.
Yeah.
Full.
Yeah. Ask Gamray. Maybe Gamray can explain
Gamray.
their modulus. Their stuff there.
If it's in their software and it says impedance modulus, one of their guys should be able to answer that question.
Maybe they can answer that, I suppose.
Sorry.
All right, I think we're gonna wrap it up here. I guess it's been over 2 hours.
Yeah.
It's been a marathon one. It's been good.
And thank you all for joining us. We're gonna have a live stream next week. Join us at the same time, and we're still playing around with some things. But for those of you who are still on, we're learning a little bit more about Restream, and we're even thinking about possibly inviting guest speakers to come on. Because you can type questions to us, but it'd be one thing to actually have you and have more of an electrochemistry discussion. I think it's great. Seeing people in the chat.
We would like to try to see if that might work in the future. So if you're a member on our YouTube channel, we might see about having you come on and you can talk to us and we can hear your voice, maybe see your face, and can ask us questions live and have more of an engaging discussion. So we'll give that a try maybe in the future. So
okay,
cool.
All right, very good.
All right,
very good.
Yeah.
All right, take care.
Thanks everybody, and take care. Yeah, we'll see you next week.
Bye.